I've missed everybody. It's been like forever since I've seen you all, so it's good to see everybody again. We are back, CS 107, and we're getting to the end. Like, the topic that we're talking about today is like the last major topic for the final exam and for your last project. And the next two lectures are going to be all on that. The rest of the quarter is basically going to be, like, the last couple weeks is going to be extra things that you don't really need to know for the final or the assignments but are interesting. We're going to have one of the TAs, or two of the TAs actually, give a lecture on some material on the file format, which we've kind of taken out of the curriculum, but still you might find a little interesting. And then we'll do some optimization. I guess the optimization is going to be on the final. So next Monday's, let's see, next Monday's class will be as well. But we are starting today on managing the heap. And if you have talked to anybody else who's ever taken this course, you'll know that the last assignment traditionally is this heap allocator assignment. And it is a pretty challenging assignment, mainly because it's there's a lot of, like, void star stuff that you need to deal with. And as we'll see today at the end of the class, one of the things you have to do when you write a heap allocator is this weird kind of inter-data structure manipulation and things that sometimes people find a little bit tricky. So anyway, today's lecture and Friday's lecture are going to be on this heap allocation. And then on Thursday morning, the next assignment goes out, and it's basically due at the end of the quarter. So that's where we stand at this point. Oh, by the way, the course reader, I'm still updating it for the heap stuff. So it's kind of updated with most of the stuff we're talking about today. But hopefully by tomorrow, say midday, I'll have the rest of the chapter completed. So if you want to read the course reader on managing the heap, I'm getting there. So it'll happen hopefully by tomorrow morning. How's the binary bomb going? You guys enjoying it? Or hopefully it's not too frustrating, I hope? Question, comment?
Is the assignment that's coming out on Thursday the heap allocator, or is there another one?
The assignment coming out on Thursday is the heap allocator. So that's the last assignment, yep, for the quarter. Yeah. All right, any comments on binary bomb? Good, bad, indifferent? It's going all right, though? The people I've seen working on it, you guys are working hard. Hopefully you've kept in mind this is a puzzle, and that's the made it doable and, like, interesting in that sense. If you are still having trouble, remember it's due technically Wednesday night, and then I think you have till Thursday night. Is that it, to do the to finish it up? I think that's the way we've scheduled it. There's lots of office hours this week, and feel free to stop by, and we'll kind of point you in the right direction if we can. The TAs generally are not really going to say, oh, remember, this is exactly what's going on at this line. You're supposed to be able to figure that out. But we can give you pointers, and we can help out along those lines. OK, look at how many things we have to cover today. Woo, program, address space, all this stuff. There's a ton of little stuff that goes along with managing this heap, which we've been using, but we haven't really dug under the hood yet. Now we're getting under the hood, and we're going to see various methods. In fact, we're going to see 3 different ways to build what we call a heap allocator. And then you'll have to do 2 of those ways for the final project. OK? All right. So what does it mean to allocate memory? Now, we've talked about this a ton already in the class, right? There's 2 different types of memory, main memory. Okay, there's also registers, which, by the way, it seems that some people still haven't quite figured out. Registers are not in main memory. They're their own part of the chip that has its own memory. There's no address for a register. Like, registers don't have addresses. You can't do a stack overflow and affect any of the registers. It's just not possible. It's a different place in the computer, so not possible. But the 2 places in main memory that we care about are the stack and the heap, as we've talked about a zillion times already. Okay? Your program has 8 megabytes of stack that it's kind of given initially and said, this is yours to use for the rest of your program. And it's basically just scratch pad. Okay? And then the heap, which is ultimately controlled by the operating system, okay, is the part where you need this heap allocator, which maintains the pointers that you request using malloc and calloc and realloc, and then you free up with free. That's what the heap allocator is doing. It's managing all that memory space for you but it's doing it for various programs as you go along. Okay? So in the heap, we have memory that is basically, you can think of it like this. We're not going to go too much deeper than saying there's this one big section of memory we call the heap, and you're going to partition it using your heap allocator to actually give various pointers into that memory for the programs that are running. Okay, so that's the kind of the lowest part of the level we're going. And what it means is you've got to allocate contiguous space, contiguous memory blocks that are either free or allocated. Okay, so if you have a space in memory that looks like this, let's say, and that is coming up there, there you go. It looks like this. If you want to give a program, or if a program requests a certain amount of memory, you might give that program a pointer to here and then know that this much memory is available to them. And then the next time the program asks for more memory, you might point it to here, and then let's say this much memory is now for that part of the, like that pointer designates that much memory. This is how it's going to work, right? And if you, let's say there was a third one here, and you would give back a pointer to here and then allocate that space. If the program calls free on a particular pointer, then maybe it's going to free this one here. What you do is you have to go back and say, oh, now this is available for maybe future mallocs. Okay, and then the next time somebody asks for some memory, if it happens to fit in this space, you'll give them back that same pointer there, and then maybe it's like this location. Okay, so that's what the heap allocator is actually doing, and you've got these blocks that are called free and allocated based on whether or not they've been requested from memory. Okay, when you call malloc, your program gets access to that allocated block, and only your program can use it. No other program gets access to it. Okay. To read and to write, and they remain, as we know, for the whole rest of your program, unless you say, I'm freeing this memory. Okay? At the end of your program, yes, the heap allocator does free up the entire block, or the operating system, I guess, ends up freeing the entire block. But remember, we want to write programs that don't have memory leaks in them, so that at the end of our program, there are no extra memory frees that need to be done. So that's the way that goes. Okay, so that's what it means to actually allocate memory. Okay? Where does the memory actually come from? So we've seen this diagram a few times. I've shaded in green a couple of specific places here. Have you ever wondered what happens when you type /program name? Most of you probably have not cared about that much, but maybe you have. When you type /program name, the operating system loads your program. Okay, and it has to do a whole bunch of setup. All right, what does it do? It actually creates a new process. That's saying, okay, there's this place in memory that's running, and those processes get put into a queue of a whole bunch of different processes that run one after another. Did you ever wonder how you can be browsing the web at the same time that Microsoft Word is open in a different page, and Adobe Acrobat's open in a different page or whatever? Or a different window? Have you ever wondered how that happens? Well, each one of those programs has a process, and the operating system cycles through the processes and says, hey, do you have anything going on? Do you have anything going on? Do you have anything going on? And it just goes one after the other really fast so that you don't notice it. But at any given time, there's really only one process going per core on your computer, and some computers have 4 or 8 cores in them. So that's another kind of subtlety to the whole thing. But the idea is that the OS loader creates this new process for you and sets it up so that it gets time sliced with all the other ones. Then it sets up all these address space segments. That's the stack, and that's your portion of the heap, and that's where all the shared library stuff goes. Okay, so it's setting all that up, all the addresses for that. Then it reads in your file. It loads all those instructions that you've been carefully going through in binary bomb. And remember, those instructions are just bytes themselves, and so that gets loaded into the program memory. It loads any global data that you may have, and then it maps into these various green sections here. So the shared libraries go in this section up here, global data is this little part down here, and then your actual program lives down in this location. Have you been noticing things like, oh, all of my jump addresses are in the 4000 range? I don't know if you noticed that for your programs, or maybe 6 in some cases, but mostly 4. And then any global variables are located in the 600 range. That's because your program got kind of put, all those locations got put there by this loader. Okay, so it set all that up. All right, then it's funny, it loads the libraries, what we call on demand. So this area here, this area over here, is for shared libraries, and it only loads those libraries when you use them. So if your program never calls malloc, it's not going to bother putting that in there. But what it actually, it's very interesting how it does it. If your program at some point uses malloc, it doesn't load it until malloc is called. And at that point, it sets everything up. And it's interesting, it puts what we call a stub in the program itself to be a kind of a dummy pointer, and then it fills that pointer in. It actually modifies your instructions as it's going along to point to the correct location later. It's not necessary if you really understand that, but it's interesting nonetheless. Then it sets up the stack, like it actually says, hey, here's the location. I guess that's kind of setting it up here as well. It sets RSP to the correct value in the stack. That's where the main gets a stack pointer. And then malloc is part of this heap allocator. It's written in C. It is not assembly language. I mean, of course, it's compiled to assembly language. But malloc is written in C. And that's going to kind of start itself up and say, it's going to call with some special parameters that's going to say, OK, now malloc is all set to know where this block is, and it's going to get one big block of memory, and so forth. And then malloc actually does that. It asks the operating system for a big memory region, which it then can give out in those little chunks we talked about. OK, so that's what happens when your program loads, which is kind of interesting. You know, see that to understand that. If you want more details on that, the operating systems class, CS140, is where you're going to get more details on those types of things. Okay? All right. We've kind of mentioned this before. Why do we even care about stack and heap allocation? Well, remember, the stack is just a scratch pad. It's a limited amount of memory. It's reused for each function, right? The stack memory that if you put any variables on the stack, when you return from the function, those are gone because the stack pointer just kind of goes above those, and they're still maybe still in memory, but they're not accessible by you anymore. Okay, it's not persistent. That's the important part in that case. Okay, but because it's already allocated, it's fast. Right? You don't need to do anything. What do you need to do to allocate memory on the stack? Move the stack pointer. Then you've got access to that memory. No, nothing else is necessary. Heap memory is a little more intense. Right? It takes time to set up the heap. Okay? You have to go through this heap allocator, which needs to do a whole bunch of calculations and things, and like figure out what portion of memory to give you and set all that up. But basically, it's unlimited. Right? For all intents and purposes, heap memory, you can use up to the amount of memory in your actual computer main memory. Like you can have gigabytes of memory. Now, most of the time, it'll be hard to allocate entire gigabytes at once, but you can allocate a whole bunch, and the operating system will gladly give it to you. In fact, it's even more interesting. If you run out of main memory, yet you ask for more, the operating system will actually go to your hard drive or your SSD and allocate memory to be used on that, and then your computer slows to a crawl because that's really, really slow. But it'll still technically work. It's just not really feasible to do that. So it doesn't crash unless you run out of disk space as well, and then you've probably got bigger problems. So that's that. All right. Heap allocators you need to write, and you're going to write these programs. You're going to actually write these. Malloc-free realloc, and then there's also calloc, which is kind of you can do that just by using malloc. But these are the three things. So let's just briefly refresh our memories on what all these do, right? All three of these functions, well, malloc and realloc, are void star functions, meaning they will just give you back a memory location. It's your job to cast it if you need to, okay? Malloc takes the number of bytes, and that's the request, and it returns to you a pointer to a contiguous place in memory that you have access to for those bytes. Okay? If it can't give you that much space, it will return null, saying it's not available to you. Your heap allocators will run out of space because we aren't giving you the entire memory system to work with. Free, on the other hand, is just a void function, but it takes in a pointer that you, at some previous time, have called malloc or realloc or calloc on. Okay, that's a guarantee from you when you're using free that you're not going to pass it some bogus pointer. You can pass it null. But notice something about this. We don't pass in how many bytes we're freeing. Right? There is no notion of how many bytes you're freeing. It's just given to the heap allocator and say free this, meaning that the heap allocator has to keep track of that. Right? The heap allocator has to keep track of the memory for each call because of the fact that you don't actually give back an amount of memory to actually free. Could they have designed it differently? Probably. They didn't. They designed it like this, and now we're stuck with it. And then finally, realloc, remember what it does. Realloc is similar to malloc in that it actually takes a pointer in that has already been malloc sometime, or null, which it kind of ends up as malloc. But it takes a pointer, and then you can either increase or decrease the size. Okay? And then it changes the size. It actually moves it if necessary. If you try to allocate an area that's not contiguous, or it doesn't have the room right there, it will actually copy and move it for you, and then pass you back the other new pointer to that. Okay? Most realloc functions do not bother changing the size when you when you realloc to a smaller amount. This was covered in a homework assignment just kind of briefly. But the idea is it's not that common to reallocate to a smaller amount, and it's kind of annoying if you have to change the things around. So they just normally don't do it. But for your heap allocator, you are welcome to do that. In fact, it's probably going to be wise based on the specifications of the assignment. Okay? All right. What does a heap allocator require? Okay, a heap allocator has to be able to service arbitrary sequences of mallocs and frees. In other words, you can't say malloc this and it says, okay, I think I'm going to have that space soon, but wait a minute, and we'll just not give it to you now, and then free a little bit later. It has to handle them in order. That may seem kind of obvious, but that's one of the requirements. And at times, if you're really evil, you can malloc a whole bunch of space and then try to reallocate it and so forth, and you'll run out of heap space because it didn't fit in with the model that the heap allocator was using. It's rare that that happens, but that can happen. Okay? Malloc has to return a pointer to contiguous memory. I'm going to keep saying that, and you'll see that in all the different diagrams that we do. And it's got to be equal or greater than the requested size. Now, why would you make it greater? Well, there's alignment issues. So if you ask for 7 bytes, it's not going to give you a range of 7 bytes. It's probably going to give you 8 or maybe 16, depending on the allocator. Why? Because it doesn't like to have free blocks that are not aligned to either 8 or 16. So that's a big deal. The payload. Now, this is a word you'll see a ton as we go along. The payload is the memory address that's pointed to when you give back that pointer. Okay, so if your program asks for 200 bytes, you're going to get a pointer, and those 200 bytes that pointer starts pointing at is considered the payload of the allocation. Why would it be called anything else, or why would it matter that there's this payload? We will see by the end of class today when that becomes an issue. Okay? Notice that for malloc anyway, you don't get zeroed out memory. Right? It can be zeros or it can be, I'm calling it garbage here, but it's interesting. Here's what actually happens. The first time you do malloc in your program, it will be zeros. Here's why. When your program first gets memory, it asks the operating system for a bunch of memory that could have been used by other programs. Wouldn't it be nice if you're a hacker if the memory happened to come to you and might have somebody else's password from some other program? So what happens is the operating system says, okay, fine, you want a new page of memory that was used by some other program? I'm going to zero it for you. That's only the first time, and you shouldn't ever rely on that. Okay? Future times, what it does is if you ask for a location here, let's say you ask for a location like right here, or you ask for a location, it gets you the pointer there, and then you fill it in with a bunch of things, right? And then you free it. Well, the next time you ask for a malloc, if it happens to fit in the same place, it's going to give you back your memory, which might have your old garbage in it. Like it might have your old stuff in it, but that's not really a security issue because hopefully you don't care to get your own password back, et cetera, right? So there might be some security issues there if you're trying to hack into it, but that's the bottom line. Yeah. Yes, very good point. So the question was, when you're freeing memory, there is no wiping out of the memory. In fact, it doesn't even change the pointer. Like, it doesn't even null out your pointer. Remember, we did that for, I think, a lab one day where he said it's not really feasible to do that. So, so it's not, yeah, you don't actually zero out any memory when you free at all. It just kind of goes, OK, well, we'll just use that. That's free now. We're going to use it later. Yeah, good question. All right. So, if the client introduces an error, like in other words, if you try to free something that wasn't allocated before, or you try to write past the buffer, or you try to do any kind of, or if you like try to malloc something with, or if you try to free non-allocated memory or use freed memory, like after you've freed it, all bets are off. Like the malloc is not going to do the kind of checks. And remember, this is what C does all the time. It's not going to do the kind of checks that you need to know for like helping you like worry about your errors, right? These can lead to really, really hard to find bugs. If you end up trying to use freed memory, it might write over something that is used in some other part of your program. You might not, or might get used in some other form. Or if you free non-allocated memory, this leads to what we call Heisenbugs, which are just like the Heisenberg uncertainty principle, like really hard to figure out, right? They're bugs that manifest themselves somewhere later, and then you come back and say, oh, it looks like Sterling is broken, and we say Sterling's not broken. Your program probably wrote over something, and et cetera. Okay, so that's a kind of an issue, but if your client does that, you do that. Now, as the malloc writers, which you will be for your last assignment, it gets even harder to track down some of these bugs because your malloc itself is dealing with the memory that the program's going to use, and if the program uses it correctly, but you allocated it incorrectly, then it's your problem, not the calling program's problem. So there's some interesting issues there as well. Okay, the heap allocator has some constraints. What are those constraints? Well, the first constraint is it has no idea how many mallocs you're going to do. It has no idea how much memory you're going to request, right? It knows you're not going to request over 64 bytes of memory, right? Petabytes of memory, because that's the limit. But that's it. It also has no idea what the lifetime of those blocks are going to be. It can't say, OK, I'll give you this for a couple of minutes, and then I'm going to take it back so that some other program can use it. No, you're good for the whole rest of the program, no matter how long your program lasts. Okay? As I said before, it has to respond immediately. It has to just take the malloc and then give you back a pointer or null, right? It can't like reorder the mallocs. It can't be, and that may seem a little silly, but in other contexts that might be important. But it can't say, OK, you're going to ask for this amount of memory, but I see later in your program you're going to free it, so I'm not going to give you that memory now. It can't do that. Okay? What it can do is it can either defer, ignore, or reorder any frees. Right? And what that means is, look, if it doesn't care to do any freeing internally when you say free, that's its problem, not your problem. Right? The heap allocator can free whenever it wants to. Now, we'll see when that becomes apparent. In fact, you'll have to do this for the assignment. You'll have to like make a decision about when you actually free after somebody frees. Okay? If somebody calls free, they're guaranteeing they're not going to touch that memory anymore. Whether or not you give it to someone else right then or later or never even bother to touch it again, that's not their problem. That's like your issue that you can deal with. So that's what some of the limitations that the heap allocator can do. Okay. So far, what other questions do you have? Yeah. Oh, such a good question. So Sheridan says, hey, look, what if you ask for a memory location, or you do a malloc, and it gives you this memory, okay? And then you go and you're like mean, and you pass back free this next byte, which is still in your memory. So I'm not going to well, it depends on how your allocator is set up. But I can tell you that the way we're going to set these up, that's going to be a really bad thing. Okay? It's going to be a bad thing because I won't give away the details right now because I want to save it for a little later to surprise you later. But basically, it's going to be a bad thing because of the way the heap allocator has to know where things are. Like you pass it a pointer, it's going to expect that it's a pointer it gave you earlier so that it knows exactly in memory where it can go find other things that tells you the information about how many bytes it is and so forth. So very good question. You'll see about that. You'll see how that works in a few minutes. Yeah, Jayla. Yeah, so this is a good question. So Jayla says, when the data is not wiped when you free it, the data is, when you have the if the data was going, if the pointer was going to be given to another memory address, it would be freed. Or another program, rather, it would be freed. For your program, it's never wiped because you don't need it to be wiped. And now, some password programs, for instance, will wipe it itself. Like if you're going to write a program and you're like, OK, I've used the password, why leave it in memory just in case? You wipe it yourself. But just know that the operating system or malloc is not going to do it for you. Free is not going to do it for you. OK, any other questions at this point? Yeah?
You mentioned that the heap allocator won't necessarily free after you call free. Does that imply that I can free my program and then let the heap allocator decide to free sometime later? I can still access?
Yeah, this is a good question. So yes, if the heap allocator decides to wait to free the memory, right, you can write to those bytes as much as you want, but you have no idea that that's the case. It's not like the heap allocator is going to say, oh, by the way, you still have use of it. Right? Now, in some other programming languages, there is a deferred kind of way of doing this, which is interesting. In C, that's just not the case. So yeah, technically, you could keep writing to those memory locations as long as the heap allocator hasn't done anything with them or given it to some other program, but you just have no idea that that's the case. So it's dangerous to try to second guess the heap allocator. Yeah? Oh yeah, so this is a good point. With flash drives, if you do deleting in flash memory, most of the time it's not deleted until the entire block is going to be reused. So that's the same sort of thing. So if you delete, let's say you have a bunch of images on your flash drive, and then you like drag them in the trash and empty the trash, the files are probably still there. So there are programs that you can get to go and recover those, and or you can send it to somebody and pay them like $500 and they'll send you back their images. But you know. Whatever. But anyway, yes, good point. It's kind of a similar idea, is that it's deferring the actual deleting until it needs to be done. Yeah, good point. OK. What other allocation requirements are there, or allocator requirements? Well, the allocator must align the blocks, or at least it does. I mean, technically, it probably doesn't have to. On some machines, it would. But on our machines, I don't think it technically has to, but it always does. Align the blocks so they satisfy all the alignment requirements or suggestions. In Linux, for 64-bit programs, it's actually a 16-byte alignment. In other words, all addresses that you get back from malloc will be divisible by 16. Okay, that's how it works. It just kind of shifts over, and if there's wasted bytes, well, so be it. Okay? For our assignment, I believe we're only going to necessitate that you care about 8-byte boundaries. But it means that you can't pass back a pointer that's not divisible by 8. Okay? And you'll be doing that by virtue of the way you're setting this up anyway. Remember this question from assignment 3? Examine the expression on line 10. Well, you don't remember what that is, but there's an assumption baked into the code. This was the malloc code. Or sorry, this was it was the part of the assignment where it was writing into it was doing, I think it was stir copy, but it was really fast. And it was really fast because it was doing 8 bytes at a time. And it could do 8 bytes at a time because it knew that even after the amount of space that you had, like malloc, there's still going to be extra space up to 8, no matter what. So it knew enough about its own system that it said, fine, I can write to those extra bytes because I'm guaranteed to have an 8-byte boundary here. So it doesn't matter. And so it has to know enough to do that. You have to be careful with that, but that's the way it works. Okay? The payload has to be maintained as is. In other words, it's not like the heap allocator on its own can give you a pointer to here, right? And then you get these bytes, and then it says at some point later somebody asks for more memory, and it says, oh, well, you know what? If I move this one I gave you earlier over to here, then I've got enough space for the big memory location, the big malloc I need for some other part of your program. It can't do that. Why can't it do that? Why is it not allowed to, by itself, move memory around? Yeah, sure. Yeah, your program wouldn't have a pointer to the right location anymore. It's not like it can like tell your program, hey, I've updated your pointer. Maybe in some other programming language it could, by the way. I mean, maybe it would. Maybe there's some dynamic way that it updates all the underlying references and so forth, and then they can move around as much as necessary. Not a bad research paper, it sounds to me. Probably been thought about before, but yeah, but that's the exact reason. Okay? The programs associated that already have allocated memory are expecting that memory location to stay the same, and so you can't like corrupt that by just willy-nilly just saying I'm going to update that. Okay? the allocator can manipulate and modify free memory all at once, right? So if it has like two free blocks next to each other, it can make one big free block. We'll see that a little bit later as it goes along. But free memory, allocator can do whatever it wants with it. But memory that's allocated, can't touch until the program frees it. Okay? All right, what are the goals of memory allocation? Well, first of all, you want it to be fast. Why do we want it to be fast? Because malloc and free are used a lot in programs. I mean, our little programs, we don't use it too much, but it's used a lot in general, and you want it to be really fast. Okay? You don't want your heap allocator to be pokey and like crawl, be really slow, especially when you've allocated a whole bunch of stuff. We're going to see one way of doing heap allocator later, which would be really, really slow if you wanted to actually do it that way. Okay? Ideally, we're talking about constant time here. Okay, we're talking about like you request it, and then it doesn't matter how many other things have been requested, you get back a pointer in constant time. Okay? If it degrades to linear behavior, and it can in some cases, depending on how you build your heap allocator, okay, that's not a good thing, because linear is slow. Right? We love constant time, we hate linear time. Okay? It also wants to try for what we call a tight space utilization. Right? That means that it's going to try to pack everything into that memory location, into that memory block, right? If you ask for a little one here and then another little one, well, it's not going to put the other little one way over there, right? If it can help it, because that just gave, like that made you have two much smaller free chunks, right? What's it going to do instead? It's going to, instead of putting it over here, it's going to try to put it right next to it here so that you've got this whole area free. Okay, it's going to try to do that. What happens when you don't do that is what's called memory fragmentation. And memory fragmentation is bad because then you just end up wasting a lot of memory, because if I ask for spaces and you don't have many of those free spaces, because you've got a whole bunch of little ones kind of dotting the whole memory location, or memory space, then it just makes it harder to meet all the requirements. Okay, this is going to become important for when you build yours as well. Yeah. Yeah, this is a good question. When you reallocate to a smaller space, yeah, sometimes some heap allocators might do that. The thing, again, it goes back to, you're trying to do this fast. Maybe it would be harder, maybe it would be too slow to try to do that with moving it to a different location or whatever. You're trying to do it fast, and it's just not that frequent that you ask for less memory. Occasionally, and you can, but it's probably not going to, right? Unless it's a giant amount of memory. Okay? By the way, while I'm thinking about it, Valgrind has its own heap allocator built into it so that it can tell when you're writing to locations you aren't supposed to and so forth. Valgrind will always resize your memory. This is also why when you run your program, sometimes it crashes when you're not using Valgrind, and then it doesn't crash when you're using Valgrind, and you're like, what's going on there? It's because you probably got something that's screwing up the heap allocator, the real heap allocator, and when you're running it under Valgrind, not the same heap allocator. So that can cause issues for debugging as well, but that's the way it goes. Okay. The heap allocator has to dole out memories that are smaller parts, and it just tries to do this really, really efficiently. Okay, we don't want to get fragmentation, and it tries to group allocated blocks together, like it tries to group them as close together as possible, and that's the basis of the space utilization. By the way, we also want to have what we call a small overhead relative to how big the payload is. Okay, we'll see what overhead really means in our heap allocators in a few minutes. But for now, just know that you don't want to have these giant structures which take care of all the, have lots of information about them if you're only allocating like 8 bytes of memory, right? You don't want 24 bytes of memory or 64 bytes of memory to be used if you're only allocating 8 bytes of memory, because that's way too much overhead. You want to limit the overhead. We'll see some of the limitations of overhead as we go along, and you'll see why it's really important when you're building your own heap allocators a little bit later. Okay. All right, what else? We want heap allocators to have what we call good locality. Okay, that's again, we want small blocks to be kind of next to each other as we go along. Okay, I've termed it like this: blocks that are allocated close in time should be close in space. In other words, if you allocate one and then another, hopefully they're right next to each other. That's one of your goals. Okay? Another type of goal, and this isn't always followed, is that similar sized blocks are going to be close in space as well. So if you have a whole bunch of little ones, put them all in this part. If you have a giant one, if you have giant ones, kind of put them somewhere else. That's maybe a strategy that you can use. Okay? By the way, there's been tons of research into heap allocation. Namely, Don Knuth, who's here at Stanford, did a ton of this stuff for the first edition of his, or first volume of his book on the art of computer programming, and he like kind of designed a lot of things. We'll talk about some of the things he did a little bit later as well, but big brains have thought about heap allocation. Okay? In fact, funny story, this was not me, I'm hearing that, I heard this secondhand, but some students who were in 107 a couple years ago were working on their heap allocators, and Don Knuth happened to walk by and was just chatting with them and said, hey, what are you working on? And they go, oh, we're working on this heap allocation assignment, and there's no TAs around or whatever. And Don said, I know a thing or two about heap allocation. What do you got? and I don't think they had any idea who he was. They just asked him a bunch of questions. He said, yeah, and answered them, and there you go. Anyway, you should know what Don Knuth looks like. There you go, if he happens to stop by. OK, what else about, what are some other goals? Other goals are like, you want your heap allocator to be robust, right? You want it to be efficient, you want all that. You also do want it, if possible, to recognize when the client has some error. Right? We don't like these Heisenbugs that take a long time to debug. So if Malik can figure out that you've done something that's wrong, it should try to give you an error message or crash the program immediately to like make it easier to debug. So that's one thing to do. Now, you will quickly find out when you write your heap allocators, this is almost never the case. If you pass in, like Sheridan was saying, if you pass in a pointer to the wrong location, the heap allocator literally has no idea whether to tell whether or not you've done something incorrect or not. It has zero way to figure that out. So if you can do it, if you can recognize some of these errors, great. If you can't, well, that's the way it goes. Okay? Like what's required to detect and report them? Well, you need to know the structure. You need to know exactly how your heap allocator is in memory. And that's kind of not even possible as it turns out. We'll see why as we go along. Okay? You also want to make it easy to implement and to maintain. Okay? One of these, you're going to have possibly lots and lots and lots of void star and void star star pointers and star bracket void star star and all these kinds of things. And if you have those littering your code, it is not easy to debug these things, right? Because void stars don't give you much information, and all of the syntax is just kind of ugly. You can prefer to type def these things. Okay? You can say, look, I'm going to have this void star, this star void star pointer that's you know this big. I'm going to type def it to some other definition that makes it much easier to understand. Okay? So you're going to do things like that and use that as much as possible. You're also going to, if you can, use structs to actually point to a location, and then if you cast a void star to a struct star, remember how structs work? You have the offsets built into the struct, and the compiler takes care of all that for you. So if you can, try to avoid too many void star star business things, and we'll get to more details about these later. Use structs as much as you can, and use type defs as much as you can, and it will become like much easier to maintain and to debug your code. Okay? While I'm thinking about it, the textbook, I think it's chapter 9.9 or section 9.9, talks all about the things we're talking about. In fact, it's a great reference. And they actually give a heap allocator program like in the text. Right? And if you want, you can start with their heap allocator and you can modify it. Now, we have different restrictions than they do, and we have different ways of doing it. You can't just take it and go. What they do is they actually have a lot of what we call macros. And we've seen these before where you have the pound define, et cetera, and it does something. They have a whole bunch of those built into their demo program. And it turns out that's not needed anymore, and it's also not a particularly easy way to go about doing it, right? Instead, you just build it into the actual code. Now, the reason I bring this up is because this conference that I went to last week, one of the authors of your textbook was there. There was a session on heap allocators, of all things, so I went to it, of course. And the question came up to him, why did you build this with macros? And he said, well, we did that like 15 years ago when it made a difference, and we haven't changed it. So that's really, it's like basically he didn't update that part of the textbook. Okay, so you can start with the stuff in the textbook if you want to. Just know that it uses these macros, and you probably should not use them because it's not necessary anymore. Okay. heap allocators, one of the reasons it's your last project is because it's kind of a capstone sort of project. It's complex, okay? Like that's just the way it goes. Heap allocators are complex, and the more effort you put into writing clean code, the more you're going to be rewarded by trying to do the debugging. You're not going to spend an extra week debugging it if it's nice and clean to begin with, okay? You will see this when we release the assignment. All right, so now all of that is like preface to say let's look at what a heap allocator might do for a program, in a program, okay? So here's a little program I've got, a bunch of variables. They're all void stars in this case because it doesn't matter, as it turns out. Void star A, B, C, D, E. I've also got one down here that's F. I forgot to put it up there. But what it's going to do is it's going to say, OK, A is going to be mallocing 16 bytes. And then B is going to call malloc on 8 bytes, et cetera. For the rest of the program, there's going to be some frees in here. And there's also going to be some reallocs in here as well. OK, now I want to walk you through a potential implementation of a heap allocator in memory. Okay, so let's see how this actually works. All right, I've also got, by the way, the stack up here, which is where let's say we're keeping all our variables in the stack, and this is the locations. And this starts out as garbage, okay, it's just the, whatever was in the stack before. And then the heap down here is, we're only getting 96 bytes. That's a very small heap, right? We're not going to care, we're not going to like make it big, but this will illustrate some interesting points to this. Okay, so the heap starts out, and right now I'm just saying, look, all 96 bytes are free. Okay, that's when your program starts. Let's say that the situation is this. All right, everybody with me on how this is beginning? Okay, let's go to A equals malloc 16. Oh, by the way, each one of these little sections in here is 4 bytes. Right, so this is location 0x100, this is 108, and so each one of these is 4 little bytes, just so we can align everything properly. Okay, so that's each one of those is 4 bytes. All right, so let's go to malloc of 16. Okay, A equals malloc of 16. Well, our heap allocator gets that request, and it goes into the memory, and it says, okay, I had 96 bytes free here. I am going to give 16 of them to the pointer or to the request that I just got. And I'm just going to put a bunch of A's in here to say that A gets that whole range. That's not what's in there right now, but that's like the whole range. Okay? One of the things we're going to do for your assignment is we are going to actually populate all the bytes that we request with the actual bytes of the request. So it's actually going to make it very easy for you to help debug it when you have to go look at memory. You're going to go, oh, there's a whole bunch of 7s. That was the 7th request. OK, I see. It's supposed to be one more over and this and that. We'll get to that. OK, what do you think is going to happen when I do malloc 8? Where would we like to put the next allocation? Yeah, right next to it. Right, so let's do that. If we do B equals malloc, and by the way, updating the pointers over here in the A and B down here. OK, and it puts B's right there, and it's just 8 bytes there. OK, well, the same thing is going to be true for malloc of 24. It's going to put the C's right there, and it's a larger area. And then D's go right next to it there. OK, and notice now we've got just this little bit free down here. OK, all right, so far, everybody with me on that? What's happening here? We've got all the stack pointers pointing to the right addresses. We've just kind of said which addresses, which locations have which variable in them, and that's that. So far, so good? OK. Now, if we do free A, okay, let's pretend that this heap allocator does actually free it. Okay, it might free it now, it might free it later, who knows? But let's say it does. Okay, if we say free A, well then doesn't that location now become free? All right, and so initially we said A equals malloc 16. If we malloc another something that's less than 16, can't we just put it right there? Yeah. If we free C, oh good, that gives us all that location. Notice something about this. Is there a way for our heap allocator right now to say, oh, look at this free zone here and this free zone here. Let's move B over somewhere else so we got this big, long, contiguous free zone? No, we can't do that because of what we talked about earlier, where you've got to leave the program the location that you gave it originally. You can't go and change it. So we've got a little fragmentation here. It's going to happen, right? You can never get like fully defragmented. It's just not going to be possible. OK, then we're going to malloc 8. Where's the 8 going to go? Right at the beginning, right? It's going to be there, and then we've got another little free location there. But that's the way it goes. OK, then we say B equals realloc to 24, meaning we're going to say we're going to pass in the pointer to here. Okay? And we're going to say, now we want B to have 24 locations. Do we have enough space to leave it here? Here's another 8, and then another 8, and then another 8, and we've already got 8. So can we fit in the 24 there? I think we can, right? So if we do that, we then have that, and we just update that. We actually get the same pointer back, and notice that B, I don't know if you noticed, but B did not change, because we just gave it back the same pointer. We said, fine. You want to have your memory big, you want more space? We've got it there for you. Shaggy.
But in this case, why would it not be better to shift B back by 8?
Why would it not be able to be better to shift B back by 8? Interesting idea. Yeah, interesting idea. You probably could do that, but what's one reason that this way probably makes the most sense? Anybody going to give me, what was the first goal we had? Yeah?
Well, you're going to have to copy over all the data, which is going to make it pretty slow.
You have to copy the data, so it's going to be slow. In this case, the fastest way to do it would say, do I have a location here? Boom, done, right? And so that's probably the way. Now, if you're really interested in space, maybe you'll do that kind of check. You'll say, oh, is there space before? Let me move everybody back, and then, yeah, you can play that little game, right? But in this case, probably not really necessary, or not going to happen because of the speed requirement or goal that we have. Very good question. Okay, how about E? Now, E is about to realloc here, and E wants 24 bytes. Are there 24 contiguous bytes where E currently lives? There are not. See, there's 8 that E already takes up, and there's another 8, and then we've got B in here, and we didn't move it, B. So now we're going to have to do what to E? We're going to have to move it if we can find space for it, right? And we go and we start looking through and we go, oh, that block's not free. We can't move it there. Not free. This little block, we can't move it there. So we're going to have to move it all the way here. Let's see if this, let's see, 8, 16, 24, and then 32. Good, we have enough space over there. So let's actually do that. Okay, so in this case, watch the pointer value for E, which is right now at 0x100. Right? When we do that, it goes over to 0x140, and now we've actually done that. Remember, realloc moves your data for you. Gives you back a pointer to the new data. Okay? By the way, what's the not good style thing I'm doing right here? I'm storing in the same point. If for some reason the location wasn't available or couldn't allocate it, I've now lost, that E ends up being null, and then I've lost that pointer. So yeah, not the best style, but in the interest of trying to make it compact, I did that. Okay? All right, and then finally, now we have void star f equals malloc 24. Do we have 24 bytes available in our address space? Well, depends on how you define it, right? There are 24 bytes, I think. There's 16 here. I'm sorry, yeah, there's 16 here, and there's another 8 here, and then there's another 8 over here. Yeah, we do actually have 24 bytes, but the problem is not contiguous, right? So in this case, our heap allocator goes, oh, sorry, out of luck. And it actually returns null, and you do not get the memory allocated. Okay? All right, so that's kind of the thing we're going to, that's the easiest way to do a heap allocator would be to do exactly this, where you have this chunk, and then you have to figure out the chunks, and you have to do things such that you can try to fit everything in as much as possible. Yeah? Yeah, this is a good question. So if you realloc E and then set it to a different pointer, E would still point to 100, but then you'd check and say, if it's not null, I'm going to now set E to the one I just got back. That's the general methodology. As you do realloc, you say, oh, OK, it's good, and then reset it to the original variable, in case you want to update the memory. Now, if your program doesn't have any ability to save the data if it crashes, if it doesn't get other space, well, then you don't bother. But in general, we like to do the check. OK. All right. What other questions do you have about this? All right, we will, I believe I put it right here. Yes, take a 3-minute break. All right, that was a 5-minute break. But we're doing all right on time. Heap allocators. Question, first of all. Yep. Do you need to do with which? No. So our heap allocator is you have one big chunk of memory that you know you have, and you have to allocate it correctly. That's all there is to it. The operating system, interestingly, the way the heap allocator works is it asks for a certain chunk of memory, and then if your program does use it and it can't give you that memory, it won't return null. It will ask the operating system to extend the memory for you. And believe it or not, it can almost always extend the memory, even though you think, well, what if there's another program there? The way memory works, and this is well beyond the scope of this class. In fact, I was trying to figure out where you learn about this stuff. I think CS 140 is where you learn about this stuff later. There's this idea of virtual memory. Your program thinks it has memory location 0xFFFFE04, but really the actual main memory, it's somewhere way, like far away, but it does a translation for you from what's called virtual memory, which is what you have, to physical memory somewhere else. So there's a layer that we're completely hiding from you, that the hardware and the operating system completely hides from you, that does that translation. So if you have a memory block like this, you can extend it like this, just because it does that translation for you. But no, we won't have to worry about any of that. Yeah, good question. All right, so any other thoughts before we go on heap allocation so far? Okay. All right. How do we actually track the information? Remember, right, free is only given a pointer, right? Free does not actually get the amount of memory that we have. So we have to keep track of that somewhere. Okay, we'll talk about a couple different ways of doing that. Okay, another question, how do we organize and find those free blocks? Right, if you go back to what we just had, like, how are we actually finding those free blocks? Right, I mean, it was easy when we were just looking at it. We go, oh, there's a free block right there, right? But I mean, you can't do that in code, right? You have to like be able to find the next free block. Right? And you can't just like walk, there's no other information like necessarily here. You have to keep track of where all the free blocks are. So that's something we have to worry about. Okay? How do we pick which free block? Somebody in the break said, hey, wait a minute, what if, why didn't we like first when we did malloc of E over here, why didn't we put it down here to begin with? It would have been like better. Yeah, that was just a design decision. Maybe it is a better design decision to put it down, down at the end there and use up all the space at the end and then wrap around at the beginning. That's another possibility. Okay, so all those are possibilities. Okay, what do we do with excess space? Well, we kind of already said excess space. You know, you either make it a free block, or if you can't make it a free block, we'll find out why that's the case later. Then you just deal with the excess space and say, okay, well there it is. You give it to the previous, like you give it to the one that requested and say, that's theirs. That's one thing to do with it. Okay? And then when and how do you recycle a freed block? That's an important consideration. Like, when do free blocks actually become free? Like, what do you do with them when they become free? Do you somehow deal with them immediately, or do you delay the dealing with them until later? We will see. Okay? All right. So one possibility for keeping track of all this information is for the heap allocator itself to have a separate list or a table or something. Let's say it was a linked list, right, that holds all of that free and in-use information. Okay, so that's one way to do it. So you have a bunch of nodes in there, and you say, okay, well, this node's the free, there's like a free block, and it's like 196 bytes, right? And then later you come and you allocate more, and it replaces that free block. It says now it's used, and it's now you're using like, I don't know, 80 bytes. And then maybe it links to another one that says, okay, now this is free, and at some location, and whatever, 116 bytes or whatever, free. Okay, that's one way to do it. All right? A separate list is a perfectly legitimate way of doing this, right? That's how you'd update the list, right? You have to answer some questions about this, right? How do you look up that information? Well, you might traverse the list. If we're talking about traversing a linked list, right, if every free block or whatever, if every used and free block has a linked list, what have we then gone down to in terms of complexity? Linear, right? We almost never want to use linked lists in real life. You should have learned that from 106B, right? But that's one way to do it. All right, how much overhead is there per block? Well, if you have these linked lists, I mean, you're going to have what? You're going to have a point. You're going to have like a pointer to the amount, to the actual location, maybe. You're going to have an amount that's free. You're going to have a pointer to the next free block or the next block. So there's going to be some overhead there, right? It might be 8, 16, 24 bytes of overhead, but there's some overhead there. Question? Yeah, overhead means if I'm allocating 8 bytes, how many bytes do I need to store the information about those 8 bytes, right? If I'm allocating a whole gigabyte, it's going to take, let's say, 24 or 32 bytes to allocate. That's not much overhead versus the gigabyte that you've asked for. But if you're only allocating 8 bytes or 16 bytes, all bets are off. Like, it's not, having 24 bytes means you've doubled the size of your allocation just in bookkeeping. Not really the best idea if you can help it. But, you know, we got to do the best we can with these. OK. So the separate list approach is feasible. Like we've kind of talked about the idea that it's a reasonable approach. OK? You have to answer all these questions, which we kind of just did, right? It is not used in practice. Like you almost never see a heap allocator that uses this linked list idea. OK? There are some special case lists that do that, allocators that do that. Maybe they happen to be on certain systems that, like, that's the default way of doing it, and they have extra memory somewhere else, or who knows. But there are allocators that do that. Valgrind is one of those allocators that does that, but that's because it needs to keep track of all this other information that a normal heap allocator doesn't. It needs to keep track of exactly where your block starts and ends, and it needs to keep track of how many times you've accessed it, and whether or not it's below or above, and it needs to make sure that it doesn't wreck the memory when you do something slightly wrong. And like Valgrind is just, it's by default got to keep all that information, so it does it this way. Okay? And it tries to manage it that way so that it can figure it out. Okay? So those are some of the reasons we like, or that's one possibility. Okay? A second possibility, and this is the one that's common, and this is the one you're going to write for your assignment, uses what we call a block header. Okay? And that block header is kind of like a node in a linked list. All right? It's got the information about whether it's free or used, and where the actual, how much data is free or used. So it's got that. Okay? But here's the tricky part. The block header is actually stored in the same memory area as the payload. Okay? And it actually generally precedes the payload, but it's in there. Okay? What do I mean by that? Well, by the way, this is a bit like, I think in some slide later, it's a little like Inception, the movie. I don't know if you've seen it, right? But it's basically like we've got this chunk of memory that we're allocating to programs, but inside that chunk of memory, we are keeping track of that chunk of memory. All right? So inside that whole big chunk, we're going to do that. Okay? Let's see how that actually works here. Okay? Let's see how that actually works. So here's our 96 bytes again. Okay? Here's our 96 bytes. And inside those 96 bytes, at the beginning of those 96 bytes, we have what we call a block header. And this block header, in this case, is 8 bytes. And it says we've got 88 free bytes ahead of us. Why is it 88 free bytes? Because it takes 8 bytes to hold that header. We don't have 96 bytes to give out to the program. We only have 88 right now. And in fact, if we did a malloc of 88, that would be perfect. We would say, OK, we'd get it exactly right there. And then we would use the entire location, and that would be all we'd be able to allocate. But we can only allocate 88 because of this header. OK. All right. Well, here's the inception part, right? The heap allocator itself has to keep the data inside the heap memory that it's trying to dole out. Okay? And it's using part of that memory for housekeeping. Now, when we have 96 bytes, like that's a little silly. Like it's such a small amount that any overhead is going to seem like a ton of overhead. I mean, every allocation you need 8 bytes of memory to allocate this, right? It's just not going to be feasible to do very big amounts of things. But normally we have like a ton of memory in your block, and you're going to be able to not worry too much about these little 8-byte blocks for overhead. But this is the overhead part we're talking about. Okay? 8 bytes are taken up with the information that there are 88 free bytes in the block. And that's what this actually means, right? 88 and then F for free. Questions on that so far? Yeah. No. In memory, at location 100, we've got the following information. We take 8 bytes. In those 8 bytes, we say that we have 88 free bytes, and we have 88 bytes, and they're free. So at location 100, if you go and look there, you will see 88 and like free, depending on how you build that into your system. By the way, the free and used, how many bits does it take to tell whether or not a block is free or used? 1 bit, right? So you're basically going to implant it in one single bit, as it turns out. You'll determine how to do that for your heap allocator. But does it make sense that at location 100, that location is part of our data structure, which we will be then doling out other parts to later? You'll see how it works as we see the more examples. Yeah? Question?
Why did you say 196
I don't know, probably because I actually originally had it as 192. It should be 96. Thank you. Good question. Yep.
What if you have a spot where you have just enough space to store a header, but not any space?
Ah, this is a good question. If you have just enough space to store the header and no space for the block, are you going to even bother storing that header? No, you probably don't even want to. You just want to make the previous block get that information as well. And you're going to have to think about these things. Remember how I said there's a lot of like arithmetic and a lot of like thinking goes into this heap allocators? That kind of corner case is a perfect one that we're going to test, right? We're going to say, oh, well, what happens if we keep giving you allocations and then there's no room for anything but your header? Well, if you keep the header there, it probably doesn't matter too much. But you can either keep the header or not, but you would have 0 bytes free, and then it seems like a waste. OK. All right, let's move on to more example here. OK. All right, so we're going to go back to our example, kind of. It's a little bit different here. OK? Here's our example. And let's look at what happens when we do malloc of 16 right now. Well, we've now got 16 bytes that are used. Notice where A actually ends up. A gets back 0x108 as the pointer to it. Right? Why? Because we've had to keep that header there to tell us that we're using 16 bytes of memory for A. Now, this goes back to Sheridan's question earlier, where she said, oh, look, what if you pass around the wrong value? What if I passed in the value here, right? Or what if I passed in the value to here for the free block? Guess what? The heap allocator is expecting that if it looks 1 block, 8 bytes before it, it's going to find whether it's free or whether it's used and whether it's like how much space. And if it's just garbage in there, the whole heap allocator is going to fall apart immediately. Right? So if you go passing around pointers to a location that is not something that the heap allocator gave you originally, it just breaks. Right? Not only that, but in this case, again, it has no idea. There is no way to tell where in memory any of these blocks are, depending on how you do it. There's no way to tell whether or not it's a free block or data, payload. There's no idea how to do that because it's just memory at this point, and it's expecting that you're going to pass back the right information. Yeah? It lives right before the block that it gave you as free or used. So you could actually test this. If you knew how the heap allocator works, you know how the heap allocator gives you a pointer when you do malloc. If you look 8 bytes back, you'll probably find information about how big that free block is. Now, you need to know how to interpret it, because or maybe 16 bytes. It's going to be a little different for every heap allocator, but it's right there, right? You actually probably would have access to that memory, too, as it turns out. But yeah, it's exactly that. It's stored in the same memory. This is the inception part. Yeah. Right.
So then, does the heap allocator need to know where the in-use blocks are? Because if you call it free, it's going to give you the pointer to 8 bytes after the
Yeah. This is a good.
I would think you would only need to keep track of the ones that are free.
So it sounds like you asked the question a little differently, but the question is, does the heap allocator need to keep track of the free ones, or does it need to keep track of the used ones? Turns out it doesn't need to keep track of the used ones at all, because it's got that information for exactly what you're saying. When you pass back a pointer, it knows that one's used, and it can then go. But then it may need to look blocks ahead to see whether or not it's going to be able to free the next stuff. We'll get to that, but yeah, very good point. There's no other, like, it needs to know that it's 16 used here because it needs to know that it goes back to 16. Like, it needs to know that it's 16 bytes that it can free. But it doesn't need to keep track of, like, somewhere else in the list of where that is. No.
And that's why, like, a double free might break it, because it'll assume that that block is in use.
Yeah. If you try to double free, that's a good question. It's going to say, I just freed it, and now it's going to try to refree it, and that doesn't make sense, and it's going to break. Yeah. Good questions. OK. All right, let's keep going here. Let's allocate 8 for B. Look at what we did, right? A is here with 16, and then we're now saying 8 is now used for B. And then we're saying, OK, we have 48 bytes left, which is free, and that's all of this stuff. OK? See how that works? This is really clever. I mean, it's cool. It's tough to wrap your head around, but it's clever. Hopefully you'll admit that. Then we malloc 24, right? And now we're doing the same thing. And every time you malloc, you have another 8 bytes overhead that you have to get because of the header for that block, right? It's actually the header for the free block that you're gonna get. But for notice that we've allocated 3 things, and we have 3 times 8, or actually 4 times 8 as it turns out, blocks of overhead right now, right? That happens. You have to deal with it. Yeah. You do have to take into account the space, the block header. Yeah, and you'll find this out when you're writing this. You have to figure out how you have to take into account the fact that, oh, I've actually got an extra 8 bytes there for my, my header. Right? Question. Yeah, you know what? This is a good question. How do you tell the difference between your header and on regular data? You can't, right? But what it means is you do need some list at the beginning. You need some way of keeping track of where the free blocks are, or at least the first free block or whatever, and then you can go from there and walk down the list. We will get to that though. But you're right, you have no idea. If you just look at a piece of memory, it could be data or it could be header, who knows, right? And it's all in the fact that this is a very well constructed like house of cards here where, you know, it's like I know exactly where every level begins and ends and so forth based on the internal structure of when you malloc and when you free. We'll see. You'll see how it works. Yeah. In this case, I'm just saying that 0x100 is the beginning of the area in memory that you get for this block. That's all. I mean, you never would get 0x100, but it's easier than putting 8-digit hex numbers. But yeah, that's all it means in that case. Sharon? Oh, if you wanted to, well, this is a good question. If you wanted to check if you were getting a correct header from free or a correct pointer from free, you technically could like keep that address in the previous address, but it still doesn't quite make sense because you're gonna it could be bogus data. It could be the exact same data anyway. Now the odds are very slim they would happen to be the same data. So maybe maybe that's something you do. You don't really want to bother with that. It's extra overhead. And you don't really want to bother with that because hopefully the programmer doesn't give it an error, right? That's the biggest thing. Cindy, you had a question?
Yeah, so assuming that you don't need to keep track of the things that are being used, but you would need to keep track of, for example, the free space immediately preceding because you have to decrement it when you start adding things.
Yes, keep going. Yeah, I'm listening. So basically, you don't have to keep track of the free ones, but you do have to keep track of the previous block to say how much memory it is, yes.
Wait, so you don't have to keep track of the ones that are used?
You don't need to keep track of the ones in use in particular. We'll see how this works. You'll see a number of different ways of how it works in a couple minutes. Maybe on Friday, but we'll get there. You'll see. Yeah. Uh-huh. Yeah, if you mallocked 5 bytes, it would just go fine. I'm just going to give you 8, and then you wouldn't necessarily know that, but it would. It wouldn't. It aligns it always. Okay. All right. Let's see. What is another one here? Let's say we try to do free A. Well, let's see what happens here. If we freed A, okay, it's still in here right now. This is before we free. Okay, what's it going to do? We're going to pass back the pointer to here, and what's the heap allocator going to do? It's going to go to the previous 8 bytes. Figure it out, and it's going to use a struct for this, by the way. Don't try to do this with void star pointers. It's not worth it. It's going to cast a struct right into there, and it's going to have the amount of space that it was given and that it was used. Okay, so that's what's going to get passed back in. Okay, and this arithmetic is just super duper important because if you get it wrong, even if you're off by 1 byte, it's just going to mess up the entire thing because you won't read the right value out of it. Okay, and what does it do? It frees it like that. Okay, and now it says, oh, I've got 16, and it's free in that location. Okay, well, what happens if we free C now? Well, C now, this is an interesting one. If we free C, okay, we are going to take the 24 bytes and we're going to say it's 24 free, and then what's right next to it? Another free block, right? So we could leave it like this. Okay, we could leave it like this, and what it means is now you've got 2 free blocks that are contiguous to each other, which is not really that efficient. A, you're wasting a block because of the header that's there for that free block, and you're limiting yourself to only having 24 free bytes here instead of 24 plus 16 plus 8 bytes available to you. Okay, because you would have all of this space if you were to do that. Okay, so we can do that. Now, you wouldn't necessarily do it right now. like when you do the free, you might not bother doing it right then. You might wait until later when you need to, like malloc, and you might go, okay, look, I've got 24 here. Do I have any more? Let's say I need 38 or something, or 36 or something. Do I have any more? And you check there. By the way, if I'm at this block, can I get to this block? How? Arithmetic. That's exactly right. You just add, right? We know that 24 plus this location here is going to give me this location. Oh, this is all about arithmetic. Right? It's all about housekeeping and keeping track, but you have to do it inside this system. So it's a little, a little tricky. Okay? When you do combine free blocks, we call that coalescing the memory. Okay? And it's important to know when to need to coalesce, and it's important to do coalescing because you are going to need to actually access, like you don't want to leave a bunch of fragmented frees next to each other. That would be terrible. Right? If you have a whole bunch of fragmented frees right next to each other, not so good. So you probably would fragment that, or you would coalesce that and leave it like that. Your job is going to be to figure out how that actually happens. Okay? We can't coalesce more than this because B is in the middle, and there's no way we can move B, so we're stuck at this point. Okay? What we just described, or what I just described, is what we call in this case, it's not, what I'm about to describe is what we call an implicit free list. Okay? It's not really, that's kind of demonstrated this way. Meaning that we have a list of free blocks, and we can traverse our list to actually look for them. Okay? One of the things about the way we've done this up here, let's say malloc is going to have a pointer to the first block. If I want to allocate space for, let's say I want 30 bytes, what am I going to do? I'm going to look at this block, and what's the first thing I'm going to look at? Well, I guess you could do either, but I'd probably look at if it's free or not. If it's not free, I don't even bother looking at the size. Right? But this one is free, and then I say, oh, is 16 less than or equal to 30? Oh, no, I've got to go on. We do a little arithmetic. We go down to this block. Then at this block, I say, oh, it's not free, so I don't even bother. And then we go, and we have to add an extra 8 there. We go to this block, and then we say, oh, that block's free. Does it have 30 or less, or 30 or more? Yes, so we can allocate it there. You see how this works? What happens to the complexity of this implicit free list? It's linear now, right? You start at the beginning, you look at the next block, you look at the next block, you look at the next block. It's not a particularly great way of doing it. But the first heap allocator you're going to write, and you're going to write two actually, is this one. You're going to write this one so it does exactly this. This is actually a relatively straightforward one to write, okay, all things considered. Okay, so we can find the next available block just by walking through the list and doing some arithmetic. Okay? But as blocks fill up, implicit free list can be slow because the linear search is not the best method in the world. Okay? It's nice and slow. All right. Let's just answer these questions, then. This is where we're going to end today. Okay? How do we track information in a block? Well, the header block is how we track that information. Okay? We hold the bytes in the block and the state, and that's all we're going to need to do in this case. All right? How do we organize and find? Well, we have to do this linear search. We have to go from the first one, start searching, and go to the last one. Okay? How do we pick which block is available? Well, if it's free and has enough space, it's available. Whether or not we want to pick that one is another story. We might want to keep searching until we find a better one than the one we just had, right? The one we just found, but we'll get to that on Friday. What do you do with the excess space? Well, if we can fit another header and still have at least a block's worth of space, then we do it. If we don't, we just ignore it, give the memory to the preceding block, and just deal with it. Okay? And how do we recycle? We make it free, and then we do this coalescing if we can. All right, that's where we're going to end today. Any other last-minute questions on this stuff? Yes?
For the size of the header, you're going to probably want to allocate 8-byte multiples depending on what size of data you need. So to figure out how much data you need to store, you're going to need to know the size of your entire memory block. Right?
You do need to know the size of your entire memory block, yes. We're going to force you to be able to handle up to 64 bits of memory. Now, what that means in terms of the actual allocation, you'll find out that it's actually, you can play some games like you're thinking about as to limit the amount of bytes you need to hold up there. Yes. Last question. can I re-explain the extra? Tell you what, come on up and I'll show you after we get done, and then I'll redo that on Friday as well. The extras. We'll kind of review this as we go. All right. See you guys in lab and on Friday.